Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Take a minute to introduce Roger Myerson. If you are not from economics, Roger is one of the most influential economists of our generation. I think it's fairly safe to say. Let me give you a few ideas of what he's done while people are gathering in. So his job market paper, which I had the pleasure to read when he was young, was about a game played on a graph. And many people here today know a lot about the social network games. And I can take you and show you how it grew out from Roger's paper to Jackson and others, and now it's a huge literature in algorithmic game theory or other areas, related areas. Before he did that, he did analysis of lexicographic fixed point theory, which later led into the concept of proper equilibrium, which was the most powerful refinement of Nash Equilibrium. I think now you are not doing this. Oh, yeah. But the lecture today will be a continuation in the literature of refinement of Nash Equilibrium. Most of Roger's well-known contributions, and for which he won the Nobel Prize, the 2007 Nobel Prize in Economics, were for the work he did on Bayesian games and applications, which led to the theory of mechanism design, auctions, and many things, applications to regulations, things of that type, which almost every paper, half of the paper in algorithmic game theory today start by citing some of the papers that he's done along these lines. Since then, Roger has done a tremendous amount of work in political science, both putting it on theoretical, formal foundations using game theory or economic concept, but also real straight work in political science. So it's a real treat and a pleasure to introduce Roger.
Thank you. Tomorrow I stand up and present a critique of the Declaration of Independence, but that's another story. This work with Jürgen Webel. We're working on a problem of refinement of Nash Equilibrium, a problem that goes back to work on the paper we're most building on is Ehud Kalai's paper with Dov Samad on persistent equilibrium. Let me advertise that I think we take that idea and I think we are generating something that's more powerful, a more powerful refinement in certain senses than that. But that I'm not convinced we've gone all the way. We've gone as far as I can see, but for example, if somebody really understands theory of index numbers of regular fixed points better than I do, and I really don't understand it. That's the mathematics I always thought was going to be relevant for this, and I'll say that now, and maybe at the end. But people who do understand it better than I do seem to think, no, our paper's about something else, but that's okay. And so there's more to do. Okay, so we won't get very far away from the Battle of Sexes game. So this is that kind of refinement lecture. I should say it's very nice to. It's what is it? It's 2013, and we're talking about refinements of Nash Equilibrium. I'm glad to have that going on, and I'm not sure why Microsoft should want me to come and talk about it. But it's not my fault. It's Ehud's fault. They hired Ehud, and Ehud does this stuff, and I had to come and talk to Ehud about it. So here I am, and I think it is important. And there might be. I cannot say that there isn't some idea here that might not be extremely valuable in a Microsoft product. And if there is, it's all Microsoft. So I waive all rights to all profitable applications of these ideas. Okay. So the Battle of Sexes game had 3 equilibria: the pure equilibria and the mixed equilibrium. It may take a little while, but I'll give you an example where we're going to have an analog where all the equilibria it'll be an analog of Battle of Sexes in some sense, in which all the equilibria are mixed. So this is not a question of pure versus mixed. It's something else. My intuition to this paper is that if this game is played only once, so the mixed equilibrium court is one where each player is 60% of the time playing the pure strategy he or she like for the corner he or she likes better, and 40% of the time playing the other one. And there's a certain symmetry that might lead you to the randomized strategy equilibrium, but I believe that, and this is just this is my intuition. I'm telling you where I'm starting, and I can't. And if you disagree, you would just disagree. But I think in societies where this game is played a lot, well, if you and I repeat a game, that's a repeated game. But I mean, a culturally familiar game is one where you and I are playing this game. This is our interaction, but lots of other people who are like you and me have done it similarly. We know the tradition. We know what's been going on. And after a while, I think they're likely to converge to either the A or the B, possibly context-dependent. Schelling's focal point effect, might say that all kinds of environmental variables might be, but we'd learn how to converge to those equilibria. And in particular, if this is just played generically, then we learn to play the AA equilibrium and the BB equilibrium in our society. That's my axiom. So I'm looking for refinements that will rule out this equilibrium but keep these two. That's what I'm looking for. It's not, to me, it's not about Pareto optimality. It's some sort of learning stability. Now, the totally mixed equilibrium is perfect in the sense of Zelton, proper in the sense of my paper, and it's stable in the sense of Kohlberg-Mertens. Ehud was asking me, did I know Wilson and Govindan's latest stable? And by the way, that's a good question. You could just say to people anytime, because they've been working very productively for a long time, and there's probably a new, on any given day, there's probably a new one. But I believe they're working in this, they've been generally working in this tradition, and so I believe that they would not rule out this equilibrium if they're staying in that tradition. There is a tradition that ruled out, and that's Kalai and Samet's persistent equilibrium is really has been for many years the one major solution concept in the literature. As I surveyed it in my 1991 book, Kalai and Samet was the only concept I knew of that for this game would say the mixed equilibrium, no, the pure equilibrium, yes, for this. Okay. But persistent, a related idea by my co-author, Jürgen Webel, with Kaushik Basu, is the idea of curb sets, and I'll give those definitions. But minimal curb sets and persistent equilibria for games that are very similar. I'm going to show you an example too that's just sort of an elaboration of the Battle of Sexes game. And I believe Samet and Kalai knew way back when that it was easy to take a game where they did something and change it in an irrelevant way, in what seems like it should be a minor way, and suddenly persistence doesn't exclude anything anymore. So my goal is to exclude the uncoordinated equilibria for more games than persistence does, while maintaining general existence of a refined equilibrium that's also proper. My proper equilibria were shown by Eric Van Dam to correspond to a sequential equilibrium of any extensive game that could map down to this normal form game. So consistency with sequential rationality is guaranteed if you can satisfy properness so we want to have a general existence of a proper equilibrium that satisfies our refinement, as Kalai and Samet did, but we want to succeed in eliminating more things than Kalai and Samet did, or eliminating something in games that they couldn't. Okay. I cannot claim that our settled equilibrium will be a subset of persistent equilibria. I just don't know. But so the claim is it gets rid of bad equilibria, or it gets rid of some equilibria in more games. It's in that sense, it's more powerful. Not necessarily. I don't have the theorem. I don't have a counterexample right offhand. There always exists a proper, and the ultimate solution concept, for which I will assert the fully settled equilibria, they will be a subset of proper equilibria. And for an interesting generic class of strategic form games, there will be a non-vacuous, a set an open set of strategic form games for which they are a proper subset of proper equilibria, that they refine proper subsets, they actually eliminate them. Okay, so let's get the formalities and let's get serious. going to start with a strategic form game. All I'm talking about is finite strategic form games, finitely many players. Each player has a non-empty finite set of strategies called SI. And it's important to keep that straight because S will always mean the set of all strategies for a player, or the Cartesian product, just S, the set of all pure strategies for all players. There's utility. Every player has a utility function that specifies his payoff as a function of what everybody does, his expected utility payoff. Delta is the set of probability distributions. Delta of SI is the probability distributions over SI. And we'll let M, which kind of looks like there's kind of two triangles there, be the set of mixed strategy profiles over the product set, which is the Cartesian product of the individual one. And so of course we can easily extend our utility functions to mixed strategy profiles in the obvious way. Everybody's randomizing independently, and this notation is your payoff when you're player I and you do SI while everybody else is doing sig op my. And by the way, I don't know, my co-author should have made me take these out, but in my game theory book, I invented a notation where bracket something meant, square bracket meant the probability distribution puts probability on one, so this formally is a mixed strategy, so that's really a mixed strategy profile, although Mr. or Ms. I is coming at the end, but anyway. That's, okay. So Nash Equilibrium, of course, is a mixed strategy profile where any one player could not gain by deviating to any pure strategy, and therefore couldn't gain to any mixed strategy either. A little O above M means the set of totally mixed strategy profiles. Okay. Let's see. So the definition of proper equilibrium is right here. It's a mouthful, but let's see what it says. A mixed strategy profile is epsilon proper in G if, first of all, it's a totally mixed strategy profile. Everything has positive probability. And you give me any player and any two strategies of that player. If S is worse than R against what the other players behaving according to sigma, strictly worse, then player I should be putting, everything has positive probability, you make mistakes. So this is clearly a mistake relative to R. S is a mistake relative to R for player I, but SI, the probability of SI was going to be less than epsilon times the probability of RI, and that's the definition of an epsilon proper mixed strategy profile. And a proper equilibrium, as I defined it in the 70s, was a limit of epsilon proper strategy profiles as epsilon goes to 0, and Van Dam, as I said, proved in the 80s that a proper equilibrium of G corresponds to a sequential equilibrium in any extensive game that has G as its normal form. I should say my definition of proper equilibrium preceded the definition of sequential equilibrium. And when I saw sequential equilibrium, I thought, you know, that's kind of what I was thinking about. And I thought, you know, I had an intuition, but this theorem was sort of what I was thinking of in some obviously completely inarticulate and incoherent way. And the hard part, of course, is in most of mathematical economic theory is figuring out how to make precise something you kind of have a vague intuition about. And Van Dam figured out that it, you know, put these ideas together. And they said, oh, yeah, I kind of, obviously I didn't know that. But for me, this theorem motivated this definition just as, even though I didn't know the definition of sequential equilibrium before, I kind of had some idea that it was incoherent, that somebody like Krebs and Wilson ought to define something, and it ought to have that property.
What was the year of property?
Probably, let's see, I published in 1977. I was working around 74, 75. And I was thinking about extensive games. I was saying, you know, it should sort of do the right thing in extensive games. And then eventually figured Krebs and Wilson defined what's doing the right thing in extensive games, and then Van Dam proved that this idea that Meyerson had, you know, kind of does the right thing, is consistent with doing the right thing in extensive games. There's a lot of work there. I'm not saying that's Van Dam's theorem. It's not my theorem, but it's a theorem that justifies proper equilibrium. And I just, as a historical aside, since it's 2013 and you introduced me as an old geezer, I should tell you that back in the previous millennium, this is an example of somebody who did something that, you know, was motivated by something that came later, and it was. I mean, anyway. Okay, so blocks. Okay, now what's new? So let's. And I thought I got this term block from Harsanyi and Zelton, but now I can't find where they used it, or maybe I made it up. But my co-author Jürgen was willing to go along with it, and so he and I call a block any Cartesian product of non-empty subsets of people's pure strategies. And any block is associated with a block game. G is the given game, and G sub t, if t is a block, is the game where you're where you're restricted to stay within your ti subset of strategies. The mixed strategies of the block game, formally we can just embed them back. MT is not the Cartesian product of probability distributions over the TIs. It's the set of mixed strategies for the whole game that happen to give probability 0 to anything outside of the TIs. That's so. MT is a subset of MS. The epsilon neighborhood, of course, is just the ones where everything has positive probability. And the support of a distribution, of course, is the support of a mixed strategy profile is just the set of strategies that have positive probability. We say the support is in a block if all the positive probability strategies are in the block. Okay. So Basu and Weibull defined a curb set, which stood for closed under rational behavior, as something where if everybody stays within it, every player, as long as everyone is staying within the block T, every player finds the best he can do over S is a subset of T. All of his best responses, all player I's best responses in the whole strategy space are within T. As long as we all behave within the block, all of our best responses are within the block. Kalai and Samet weakened and strengthened. Their work was earlier, and they had a concept that's pretty damn close. And actually, we kind of follow their idea a little more closely than Weibull's curb set idea. On the one hand, they're only asking that within T, player I should be able to find a best response. So that's weaker than this condition, saying all best responses within T, just some best responses within T. But we want that to be true for every strategy, every sigma in an epsilon neighborhood of MT. That is, you're allowed to make epsilon probability of doing any one thing outside of T. So that's a stronger condition. We want. So they're not strictly comparable. Well, maybe they are. Let's say any curb set is absorbing. I'm wrong. They are comparable. A curb set is absorbing. Okay. So an absorbing block, and an equilibrium is persistent if it's contained in a minimal absorbing retract. A minimal absorbing block. They use the word retract, but and in fact, any absorbing block contains a proper equilibrium of the original game, and therefore there exists at least one equilibrium that's both proper and persistent. That's Kalai and Samet's result. As advertised, persistence for the Battle of Sexes game, take a quick second to look back at the Battle of Sexes game. If we're both playing our Bs, or there's with all probability almost one, then both of us for sure have a best response to play his or her B, therefore it's an absorbing set. And you can't get any smaller than 1 by 1, so it's a minimal absorbing set. So of course, the totally mixed strategy profile, which has support on the whole game, is not contained within in any minimal absorbing set, and therefore it's not persistent. But the pure strategies are. So here's an example, which is probably I think you had maybe we've reconstructed one of your examples exactly, but maybe it's the spirit, but I forget. We take one of the 0, 0s and we unfold it into say, oh, that if they play A and B, if player 1 plays A and player 2 plays B, they don't actually get 0. What they do is they go off and have a subgame where they it's a 2-person zero-sum game subgame that happens to have a unique solution, a unique equilibrium, where the payoffs, the value is 0 for both players in this 2-person zero-sum subgame. That shouldn't make any difference, but it does. It makes a huge difference. So the equilibrium sort of unfold this. What is it? The A1, A2 equilibrium. Now player 1 could randomize between. I'm taking that game and I'm putting it back into normal form. When basically, if you're going to do B, then you're not going to get into the subgame, so it doesn't matter if you're player 1. But if you're player 1 and you do A, you have to plan. If I get into the subgame, do I play it the X way or the Y way? Well, the answer is as long as I don't go more than 3/4 or 1/4, more than 3/4 to here, or more than 3/4 probability here, any randomization in the middle of this will leave player 2 thinking that she can't profit by going for one of these 2 4s. She wants to want one of those 2 4s. If she knew where I was going, she would. But as long as I randomize, it doesn't have to be half-half, but near half-half, then she doesn't want to go there. She wants to go to the A, and it's an equilibrium. But so our 2 pure strategy equilibria have become kind of, they're mixed, of course, but they're no longer so I should say our proper equilibrium, this is important. The proper equilibrium requires, the proper equilibrium is going to have the property that if you, that you're going to do the right, that even in this game, even if it has 0 probability, you do the right thing in the subgame because it's sequential equilibrium. If we found ourselves in the subgame, we should play a subgame perfect equilibrium. Sequential implies subgame perfect. So of course they have to be playing 50-50. And so the mechanics of the definition I gave of proper equilibrium, it takes a while to see how it works, but with that definition, in fact, it discovers, and it says, for proper equilibrium, you have to randomize 50-50. Why is that? Because if player 1 didn't, I'm looking at equilibrium where player 1 randomizes between these 2 and player 2 does that. That's one of these equilibria. It's an equilibrium as long as we're anywhere between the probability of the top one being between 1/4 and 3/4. But if it were not 50-50, then whichever one has more probability, let's say this one had more than 50% probability, then between these 2, but it's just a little more than 50%. Then it would be a mistake for player 2 not to do A2, but this would be a better mistake, and this would be a worse mistake. It would be a mistake. Why was it a mistake? Because you might get the 4, you might get the -4, but if player 1 is using this one more frequently, going here more frequently than there, then getting 4 more frequently than -4 is better than getting -4 more frequently than 4, with a greater probability than 4. So of course, this is the better mistake than that, and therefore it should have infinitely more probability. But the distinction between these 2 doesn't matter unless player 2 is making a mistake. And if she's making this mistake much more likely than this mistake, then player 1 strictly prefers to get that 4, which means he goes down and it goes away. So that, I've just told you the story of why proper equilibrium says if player 1 were not choosing exactly with equal probability these 2 actions, then player 2's would put much more, the small probability she put on mistakes would be much smaller for the worst mistake than for the not so bad mistake, and that would make player 1 want to reverse his priority, and therefore it can't be a proper equilibrium. So proper equilibrium narrows things down. But the only curb set or absorbing block is the whole strategy space. I just assert because the two pure strategy equilibria that used to be, if I were only in this set, this is what we're hoping to stay in. No, then within this subgame, within this block game, there are 2 pure strategy equilibria, but those are not equilibria of the original game. If I went up here, player 2 would prefer to go, would want to go get the 4. So it doesn't work. So here's what are we going to do? Let me just try to summarize what I think we're trying to do at this stage where I've shown you there's a problem, and I'm taking my initial intuition, and it all needs to be formalized in the next few slides. Okay, I want to say in familiar games, our approach is that in familiar games, what's going to really happen is some players are going to think of some strategies as being conventional or normal, and then they only think, if it's a culturally familiar game, a situation that people play a lot, then what's going to happen, we conjecture, we suggest, is that people are going to simplify the problem, think of some strategies as conventional or normal, and others, and then they just don't even think about the others most of the time. Conformity with such norms simplifies people's decision-making, and life is complicated, so I need things simplified. Let me say, Leo Hurwitz suggests that any institution in life, is really sustained in a larger game by viewing some unconventional actions as illegal. And Hurwitz's end-of-life essay, this was his Nobel lecture, that that was based on the idea that a theory of how do we sustain institutions is really a theory of there's a larger game. We don't have to behave according to our institutional rules. In behaving within the institution, we agree not to, if we're playing the institution of chess, we agree only to make the chess moves. In fact, it's physically possible for either player at any time to just knock off all the pieces. And we have this meta game where it's, you know, if I do that, you then in the real game of life, you'll treat me as, I'll be treated much worse by you for the rest of our lives. That I got mad and knocked the game over. So we only move the rook the way you're allowed to move a rook. And but it has to be, you know, so we assume that such social conventions develop in accord with the following principles. One is the rationality restriction. When people are generally expected to act rationally within the conventional norms, unconventional alternatives should not be advantageous to them. So once we, and the other is the simplification imperative, that conventional norms will tend to simplify the game by excluding as many strategies as possible subject to the rationality restriction. And we're going to try to get simpler and simpler views. Those are our axioms. I have some intuition behind them, but I'm not deriving them from anything. But I've added a word. The word rationally here is the word that I've added that is going to enable us to go beyond Kalai and Samet. We can relax the definition of curb set and absorbing sets by applying their best response conditions only at Nash Equilibrium of the block game. That's it. That's the idea. So it's 2:30. I should have gotten this. It's 25 minutes in. I should have said this in the first minute. We're going to relax the definitions of these curb sets from Basu Vebel and Kalai Samet absorbing sets by applying their best response conditions only at Nash Equilibrium of the block game, because we're saying when people are generally a curb set or absorbing set was when people are generally expected to act within the conventional norms, unconventional norms should not be advantageous. But I just said no, rationally within it. So rationally means they're maximizing given what others are doing. Relaxing the rationality restriction by adding this word rationally in there allows us to admit more blocks as conventional norms, and then the simplification imperative is going to say that when we go to a minimal admissible blocks, we're going to get a stronger equilibrium that can exclude more things. That's the whole roadmap. Now let's go do it. And by the way, I forgot to say my notes are now, these notes, I just posted them exactly as they are online on my webpage. And they have evolved, as I just posted a revised version of them a few minutes ago. They're ahead of the paper. The paper on Jorgen and my web pages has different concepts. There are a lot of different ways you can do what we just said here. There's a lot of ways to formalize it, and we have torn our hair out trying to figure out what is the 1, 2, 3, 4, you know, a small number. I'll give you 3 definitions. What are right ways to do it and you don't want to hear all of them, but on the other hand, I can't tell you I know exactly. But I think we're getting, I now think, today I'm going to tell you something that's the version of this that's most worth talking about, but there are other versions, and we've explored them in print. Okay. The paper, when we reconstruct, the paper that exists has random consideration set games in it. Now I think I want to elevate it to the main theme for this. So the main theme, we're really elevating. So we want to assume that players are very likely to consider only the strategies in some conventional block. A block that's being thought of as conventional, but they might see more or less of the game. So a random consideration set game in general is defined by a vector of profile of probability distributions, one for each player, where each mu I is a probability distribution over what's CSI is the set of all non-empty subsets of player I pure strategy. C for consider. C stands for a consideration set. You're in the game. Physically, you have a certain set of things that you can do, but maybe you don't think about all of them. You only consider some of them. You just ignore the rest. And which ones are you considering? Well, mu is a probability distribution. And so consideration. So the interpretation is each player is only going to consider strategies in some independent random consideration set that's a subset of his a non-empty subset of his pure strategies, where the probability that what he considers is a subset Ri is mu I of Ri. Okay. So now you have a game which says you know what you're considering, and a mixed strategy profile is a probability distribution that defines, given what you're considering, what are you going to do? So it's a probability distribution over Ri. And then we could say, and I'll say, of course, things that are outside Ri get probability 0. And yeah.
distribution over my restrictions, considerations.
Exactly. So it's defining a derived game structure. Given the real game, G.
Does the player know it?
We're going to analyze it as if it's common knowledge, but then we're going to look at sequences of these things. So yeah, I'm defining a game, and when you think about that game itself, you're going to think about it as if it's common knowledge. That's right. Which is ridiculous because you're only thinking about a subset of strategies, but suddenly you know everything you need to know about everything else. And in equilibrium, that means you know the distribution of other people's behavior. But I'm not going to disallow you from knowing everything about the distribution. But of course, all you care about is their actual behavior, which the equilibrium object will summarize. But yeah, so we're going to analyze it as if it's common knowledge, although that's a ridiculous assumption. But it isn't. It's more than is necessary. I said that better than I think I should have. I don't know. Anyway, let's go on. Okay. Alman must have said that. Anyway. But given any in this dumb random consideration set game, you can obviously reduce. If tau is an equilibrium, is a strategy profile, and a tau super mu is the projection back onto the original game, where you say all I really care about is what's the probability of player J. That should be a subscript J. Fix that. The probability that player J uses strategy S sub J is, well, you sum over all the consideration sets. What's the probability he considers that, and what's the probability he does Sj when he considers this? And of course, if Sj isn't in Rj, then the Rj's for which Sj isn't in it, that product is 0. So this is the marginal probability and that's all that anybody cares about. So tau is an equilibrium of a random consideration set game only if in the original game, this is awful looking notation, but this dot is saying you're randomizing, you recognized Ri, and you're considering Ri, and this is the behavior you have over the options in Ri. You understand in the original game that everyone else is behaving according to their marginal distribution, and you're going to put probability, your expected payoff is going to maximize over Ri the best you can do within the things you're considering. And that's got to be true for all Ri's that have positive probability, I guess. If they have 0 probability, I won't worry about what you do there because nobody else cares about it. So fact, for any sequence of random consideration set games and taus that are equilibria, such that if the probability of my considering tau goes to 1 and tau is an equilibrium of the random consideration set game, any limit of the marginal distributions is going to be an equilibrium of the block game. Yeah, of course. So any block game, of course, can be expressed as a limit of such things with a constant sequence, I guess, that you always yeah. So these guys are.
The definition. How is an equilibrium even only if there's a quantifier on the
power? No. You know, if you have a sequence of block game of random consideration set games where if the probability of the block T is approaching 1.
No, above it.
Oh,
definition.
This is the definition of so this I could write it a variety of ways. The way I've written it is when you are recognizing R, the way you behave gives you an expected payoff against what everyone else does, which can be defined in the original game because it depends only on the marginal distribution of what everybody else does. It doesn't matter what they're considering, it doesn't know what they do. And that's derived in the obvious way from how their behavior depends on what they consider. That should achieve the maximum against the same behavior over all the things you have available in Ri. Yeah.
All
yeah, that says whatever you're considering, you're only putting positive probability on the things that this implies, well, because this is an expected value. This is an operator which is linear in how you put the probabilities on the different things. So this is saying you're only putting positive probability on your alternatives in your consideration set that are optimal within the consideration set against. They're not necessarily optimal in the whole set because you're not considering the other stuff. And then if you take a limit of these equilibria, where over a sequence of random consideration set games where the probability of block T is going to 1, then of course ultimately everyone's just doing something that's optimal again in T. They're not doing anything outside of T in the limit because they're never considering anything outside T, and within T they're behaving optimally against what the others are doing. So it's an equilibrium of the block game. It's not necessarily an equilibrium of the original game. the result is going to be, if that limit is also an equilibrium in the original game, then it's a good block. So let's say that idea. A block is coarsely tenable if there's a positive epsilon, so such that for every random consideration set game that puts at least 1 minus epsilon probability for every player on the T block, everyone is probably within epsilon thinking about T. And we have, and for any such game, and for any equilibrium of that game, of such a game, we must have what they're getting here, which is optimal within T, is also optimal within SI, where remember SI is the name of the full strategy set in the original game, which means that when players are likely to act rationally within the T block, the probability of anybody thinking of anything else than the T block is less than epsilon, anything other than the T block is less than epsilon, then nobody can do better by choosing a strategy outside of T. That's when they're likely to behave rationally. That's the definition. And this is what we're going to call coarsely tenable. It's called coarsely because we're going to have another finally in a little bit. And the block of pure strategies. Now this, let me just check, because I just wrote this in, and I think this is my first time using the slide since we rewrote it, and I think this belongs in here. I wrote something last night, and it was wrong, and Jürgen corrected me. So let me just pause. I'm pretty sure this is right, but this is one thing I just added. It should be obvious that if you take any strategic form game, for each player, eliminate anything that's weakly dominated by another mixed strategy. Now, that you know, what do we call that? The weakly undominated residue. That's a block. It's a non-empty subset of every player's pure strategy set, and that block is coarsely tenable. I think it's obvious because, you know, for any random consideration set game, when you maximize over when you're responding to the other players and you're optimally within the weakly undominated, then you can't do better by going to a weakly dominated, because whatever you were thinking of, it's something that it must be weakly dominated by something, and it must be weakly dominated by something that can be constructed out of the weakly undominated ones. I think that's right. You always have a best response in the weakly undominated strategies, and that's it. At least for a finite game, these are finite strategies basically. So this is true, I think. If T is coarsely tenable, then the Nash equilibrium of its block game are all Nash equilibria of the original game. That is to say, that's the and the proof of that is pretty easy. If something were not, then the sequence that just always puts T with probability 1, and you play that equilibrium would fail to satisfy this equation, because you could do better outside. Now, if T is coarsely tenable, there exists a proper equilibrium of G that has support in T. That's not so hard to prove, but the proof of that will actually be embedded in the next solution concept. So now I'm going to say a coarsely settled equilibrium, I like the word settled, is any Nash equilibrium of G that has support in some minimal coarsely tenable block T with no course that, you know, minimally means that there are no coarsely tenable subsets. So that's there. How do I know there? Well, there exists a coarsely tenable block, and there are only finitely many blocks, so there must be at least one that has no coarsely tenable subsets. And by the way, you can always find one that doesn't include any weakly dominated strategy. So, yeah.
The section of coarsely tenable is coarsely tenable?
No, because it could be empty. And in fact, even if it's not empty, I can't guarantee it. No,
The minimal coarsely settled.
And in fact, it certainly is not. No.
A minimal coarsely settled.
Fine, a minimal. I don't. Yeah.
Coarsely settled.
But by minimal, so minimal, these are partially ordered by set inclusion, so it should not have any proper subset, any included subset that's coarsely tenable.
Tenable, is that obvious? Oh, yeah, it's fine. Yes, okay.
They're finally many, and it's a partially ordered set by inclusion. And lots of blocks are not comparable, and it certainly is not true that the intersection of two coarsely tenable is coarsely tenable. That's here's go back to example 2, which was carefully chosen so that persistence, first of all, didn't work, and you wanted something more. Coarsely tenable does work, but it just barely works, and you're going to be able to. So how does it work? What you'd like to say is, could I please have this set be coarsely tenable? But it's not. because, well, one way to see easily that the set where player, because we had an equilibrium players are random, we had equilibrium players are randomizing here, equilibrium players are randomizing here, and then there's a totally mixed equilibrium. And then there's, I didn't list them before, but it's the totally mixed equilibrium. We'd really like to get rid of the totally mixed equilibrium and just look inside here, for example, or up here. It doesn't work. Let me look back at it. So I said something that was obvious. If T is coarsely tenable, then all of its Nash equilibrium of the block game, all of the Nash equilibria of its block game are Nash equilibria of the original game. Well, if this set here, player 2 doing A2 and player 1 doing one of his two A strategies, if that block, let's just play the A stuff and forget everything else. If that was a coarsely tenable block, then all of its Nash equilibria would have to be Nash equilibria of the original game. But of course, there's two pure strategy equilibria at the end, which are not Nash equilibria of the original game. You have to randomize and keep the probability of either corner less than 3/4. Because if I were going this way for sure, and I'm player 1, you player 2 would prefer to go to here. But if you were going to BX2, but then of course I'd prefer to go BX1, AX1, and we wouldn't be. It's not an equilibrium in the original game. So it doesn't work. But if this set here is a coarsely tenable block, and so is this, their intersection, of course, is this set, which is not coarsely tenable. It has a unique equilibrium, which is not an equilibrium in the original game. So so you see it works, but these are kind of a little awkward. So we need something else. But do we need something else? Maybe it's just working. No, it doesn't. Because if I go both sides, if I unfold the other 0, it all falls, it all falls apart. Because now, in order to keep player 1 here randomizing, not going too far in one, if this is not a coarsely tenable block, because I need to keep player 1 from going one side or the other side too far, so I need to add these strategies in, but then I also need to add these strategies in to keep player 2 randomizing in the appropriate way. What are the equilibria? I guess the Q go between 1/8 and 7/8 because there's the 3, 2, and the 2 is different from the 3. But anyway, I claim this is what as long as you stay away from the corners, randomizations here are, and you need to add in these. You have to be aware of these other strategies to stay away from to get the word that we have to stay away from the corners. So somehow, the way we analyze a block does have to take into account something outside of it. Let me remind you, subgame perfection requires 50-50 randomization, and these two off-diagonal things represent subgames, where if we don't choose either both A's or both B's, then we go into this two-person zero-sum game, subgame, and that has a unique 50-50 equilibrium randomization. So the proper equilibria in here are 50-50. And that comes from looking outside here and recognizing that when you're when I'm only considering AX or AY, the A and X, AY are coming from, they only matter in a subgame that's outside the block, but I have to worry about it. Anyway, so something has to be brought in about rationality outside the block. We just, coarse tenability leads us no way to exclude the extreme pure strategies in the A1, A2 block without adding in all the strategies. That's the problem one. And then, of course, we're back in the original problem. But imposing some rationality on the out-of-block deviations could narrow the scope to proper equilibrium without enlarging the block. And so what our solution is to impose some rationality on out-of-block conjectured behavior. Yeah.
So the intuition you're trying to get is you're comfortable with the idea that players should randomize between AX1 and AY1.
Yeah.
It's just that your current definition
Doesn't, yeah.
explaining that randomization.
Yep, yep.
Make sure that they randomize.
Yeah. Brilliant idea. But it just comes about, could we talk about, instead of people thinking of focusing on randomized strategy, I'm thinking, what people are going to do in this game is they're going to say, I don't even think about AX, right? I just think A and 50-50 XY. I don't know. If that's a good paper, I hope you'll write it. And refer to our paper. And it might be a better paper. But we'll have prepared the way for it. somebody has to write an ugly paper that you write the beautiful paper that then makes it all simpler. But anyway, so here's what we're going to do. The random consideration set structure, I hope you'll like this. We have a definition that we've written in a variety of different ways, and sometimes not necessarily equivalently. As I told you, how exactly to formulate it is hard, because there are a lot of options, and we're just going to, I'm telling you, you'll be relieved to know I'll only tell you about a subset of the ideas we've thought about, but as anybody in any research has to do, figure out what to leave out. I think the random consideration set perspective gives a good way to make this way seem natural, and if it seems natural, it probably is. I'm going to talk about an epsilon proper random consideration set game. It's really the distribution that makes a random consideration set game, and the probability is proper. This is related to my idea of proper equilibrium, but it's on a different object. The random consideration set game is epsilon proper on T if, first of all, for every player I, the TI part of the block is getting, the player I is considering his block T, his part of block T has probability at least 1 minus epsilon. That's one thing. And for every pair of two possible consideration sets that he might be considering, such that they're both non-empty subsets of SI, and QI is smaller. If QI is not TI, and it's not RI, this is a proper subset, then, first of all, everything has strictly positive probability. That's one of the things we're putting in proper. Every possible set must have strictly positive probability of being the set that I'm considering. But when I'm not considering, and I'm probably considering TI, but if I'm not, for any two sets, the larger one is much more likely than the smaller one. Well, TI is smaller than some sets, and it is very likely. So in that case, so the idea is the normal thing for us to do is to consider TI. But if I don't consider TI, and if I'm behaving in an abnormal way, I probably see everything. I'm not behaving conventionally. I look around, I wake up, and I stop behaving like one of these conforming quasi-robots, and I look around, and I probably see everything, but I might miss something. But it's epsilon for any set that I could see. Any subset of it has probability less than epsilon times that, except for TI, which of course is what the slavishly conventional people see. When players consideration says very likely to be TI, but he might consider other non-empty subsets, any non-empty subset with positive probability. But if it's any set less other than TI, then it is much more likely to be a larger set. So then I'll say it's finely tenable, the same thing, but I'm only going to consider these proper. So if the block T is finely tenable if there's some positive epsilon such that for every equilibrium tau of every random consideration set mu that is epsilon proper on T. So it's putting almost within epsilon of 1, probability 1 on T for every player. And when it isn't T, any player who's considering something else is probably within this epsilon ratio sense, probably considering larger sets than smaller sets. And then if when we consider those equilibria of those random consideration games, when they're within epsilon, when for any mu that's epsilon proper, and by the way, if it's epsilon proper for it's also epsilon prime proper for any strictly larger epsilon prime, because epsilon only appears on the in that way in inequalities. Making epsilon larger will just strictly increase the set of epsilon proper consideration set games on T. Then we must have that, as long as we're within some epsilon proper random considerations game, all of its equilibria satisfy that the property that when you're within T, you can't do better than by going out to SI, where it's important for me to remind you SI is the set of all strategies in the original game. That's what that says. In fact, any coarsely tenable block is also finely tenable, because in coarsely tenable I was considering all sequences of random considerations at games that put probability 1 in the limit on T. And here I'm only considering the ones that also satisfy this additional restriction. So they're more finely, I'm asking less things finely tenable, and therefore I get more finely tenable blocks, but then the minimal one is going to be a finer set. And then I'm going to say any limit as epsilon goes to 0 of equilibria of random consideration set games that are epsilon proper on a finely tenable block is a proper equilibrium of the original game. It's an equilibrium of the original game. In fact, it's a proper equilibrium of the original game because we made sure when I make a mistake, it's because I'm not considering everything in TI, obviously, because once I'm considering everything in TI, it's optimal. But if I'm not, I'm much more likely to be, if there are two mistakes, it's because I'm not considering everything in TI, but I'm much more likely to be considering both those possible mistakes than only one of them. And then, of course, I would only do the one that's better among the two if I do either of them. So it's not going to be. It's much more likely that in the limit that I should do the less bad mistake, and so we get. So that's the basic definition and it is always a proper equilibrium. And now we've proven, by the way, since any coarsely tenable set is finely tenable also, and these limits of these equilibria are proper equilibria, we have the theorem I gave you before that any coarsely tenable one has a proper equilibrium. But of course, I'm now advocating look at the finely settable. I'm going to say finely settled equilibrium is any proper equilibrium that has support on some minimal finely tenable block, and then I'll say a fully. But of course, you could always go first to a coarsely. There exists a finely settled equilibrium that's also coarsely tenable. You just have to go to a minimal coarsely tenable block, and then inside of it look for a minimal finely tenable block that's included inside that. And so we call that fully tenable, fully settled. A fully settled equilibrium is any proper equilibrium in G that has support in some minimal finely tenable block that is itself contained in a minimal coarsely tenable block. And these things exist for any finite game. Okay, so now I've given the definitions. There's more to say, but you now know everything in principle. It's just a matter of exploring the implications. Question?
Just one thing, what you said about the robots.
Yeah.
It's a slightly simpler definition that seems like it might still work. You give like probability of almost epsilon to the whole game, and then maybe negligible probability to everything else. So it will be 1 minus epsilon for.
I have to give probability every. I do need to rank all mistakes, including. So certainly, the way we initially were constructing it was rather more specific by saying something like an obvious construction is saying there's some probability that you'll recognize each strategy, and we'll make those probabilities close to 1, which means you're almost surely going to see everything, but you might miss things. There's a bit of a difficulty. My consideration, since we're not going to allow me to consider nothing. Jürgen, I totally missed this, and Jürgen just said, "What are you talking? What's the word independent going on in there?" I can't independently consider my strategies independently because I can't consider nothing. I have to have something that I'm aware of. Yeah. The problem is this definition is a bit of a subtle one because there's one thing that we're saying that if what you could think is the following. With probability 1 minus epsilon, I observe TI, and then if I don't, that epsilon probability, there's this, in that epsilon probability event, now I go into another process where with probability 1 minus epsilon, each action is observed, is considered, is taken into consideration with probability 1 minus, conditional in the event that I'm not just considering TI. There's a 1 minus epsilon probability that I'm considering each action independently, and at epsilon probability I'm ignoring it. Except that the epsilon to the number of strategies event where I don't consider anything, then I go back and I behave conventionally. I don't know. So it's not. I can't quite talk. That's a bit of a mouthful, but that's something like that was in our paper before. That's a good example of one of these things. Maybe it's the only examples we should talk about. I don't know. Yeah.
Condition makes sure that the strategy is completely mixed, right? Because I can.
Yes, that's right. Yes, that's right. Yeah, absolutely. Every strategy has positive probability. Every singleton set has a positive probability, and when you do it, when that's all you're considering, you do it. That's right. So we're guaranteeing that everything is possible. That was in the original proper equilibrium definition. This here, that this is a funny way of extending my old terminology because I'm applying it to a very different object. But as you see, one of the things it does right away is it makes sure that every pure strategy has a positive probability, because certainly when that's the only one the player is considering, that's what the player must do. Yeah. But it's a very small probability because it's stacked under, it's epsilon less than probability than so many others.
This is the assumption basically that gives you the power to prove that it's a proper equilibrium.
Oh yeah, absolutely. No, of course. This definition was set up so that it would do that. That's right. Yeah. Yeah. And you know, in some sense, maybe that's what I was thinking about. You know, when I came up, I don't know. There are a lot of things you could think of today that I could claim I kind of had that intuition, but I was inarticulate about it. And so actually, that's a pretty good thing to. That's a game. I like that. That's a rather self-serving game, isn't it? I should not be proud of doing that. Oh yeah, I kind of thought of that, but no. But I'm trying to be nice about it, saying these future people are really figuring out what I meant to say, but was obviously unable to say, and not. If you can't say it, you don't deserve credit for it. I'm sorry. That's okay. So this does the trick. It has no, we saw this has no. This is the game example 3 I showed you before. It has no coarsely tenable blocks other than the whole strategy space, but the right things. This is minimal is a finely tenable block, and it is a minimal finely tenable block, as is this one over here. And we get and the solutions, the two finely and fully settled equilibria are the subgame perfect randomized strategy equilibria, the proper equilibria in those 2 blocks. And let me remind you, if when we're living in this block, if player 1 thought that player 2 if player 1 was expected to put more probability here than there, then when player 2 doesn't have these, but is only considering these 2, which is the only way she'd ever consider either. They're very close to 50% probability, but not exactly, a little more probability up here. Then she would prefer this, so she'd prefer BY2, but then that would say that player 1 would realize that she tends to make a mistake in some way that hurts me more often. When she makes a mistake, these don't matter, but when she makes a mistake, I do well with this one and badly with that, so therefore I should not be doing this, I should go this way. And so you can't have such a, so putting the epsilon, putting rationality on the trembles gets us, and saying that when she makes a mistake, she has both of these available. Obviously, if I just allowed any random consideration set game, I could obviously force her to have 50-50 probability in those 2, and then player, then she's just going to be when she doesn't see this, she does these not 50, she has equal probability on these 2 consideration set games and no probability on anything else. And then of course all she does is when she goes here, she randomizes 50-50, and then he can put more probability here, but the properness kicks in. Okay, so here's an example that's kind of important. This is the forward induction literature, and this relate in a way that we don't really understand to the forward induction literature. I noted that let's see. So what's this game? This is another version of the Battle of Sexes game. We changed some numbers, but player 1 has the choice an outside option to get 2, or he can, if he doesn't, he can go this to choose it. If he chooses the others, then he goes into another kind of Battle of Sexes game, and it has a Nash equilibrium up here, which the forward induction people like, and this gets the idea that I think we would focus on the B1, B2 equilibrium, and therefore I choose C. That exists, but formally the Nash equilibria that correspond to that say you have to have at least you can have at most 2/3 probability on A. You have to have at least 1/3 probability on B2 in order to make player. But obviously, if you go all the way to P equals 0, then this is saying that's this corner here. So the unique minimal coarsely tenable block is the A1, A2 corner. But C1, B2 is finely tenable. So this is an example where, and I don't know how I feel, I have to tell you, a lot of people really like Kohlberg-Mertens stable equilibria and related ideas. I think I'm not one of them. But I recognize that smart people do like it, and you know, this is just, you know, do you think this is? So I don't know. So I kind of like the fact that finely tenable, finely settled equilibria include both of these. But if you like stable equilibria, and many of the smart people in the audience might well feel that way, and I got to respect that. You might think if this settledness is doing any good, somehow the fully settled is picking it up, and that's so okay. That's not, and a lot of the stuff in the talk in Kohlberg-Mertens stability is about elimination of weak domination, and coarsely settled is kind of grabbing at that in a way. But I'm being incoherent because I don't really have any theorems, and I've tried to find some theorems, and I couldn't get them. But I didn't try that hard, so you try. I don't know if this example is, I don't know how interesting this one is here. I just, instead of the 4 4s, I changed some of it to 1 minus 1, so the player is not tempted. The player is getting the plus or minus 1 is not tempted to deviate. And now so this block here, this block here now is coarsely tenable, because just staying in here, no matter how, for any equilibrium in here, you know, they can randomize any way you like over these 4, over this 2 by 2 block game, and nobody's going to ever want to deviate to get plus or minus 1. But up here, it's not coarsely tenable, because if you just randomize any which way, you could end up, well, for example, going to a corner, in which case somebody's going to want to go grab the 4. Either, you know, both of them are going to want to grab a 4, actually. So in this one, there are two finely tenable. There are two finely settled equilibria. The right 50-50 equilibrium up here, and the right one down there. But fully settled only grabs. Let's see, where does it say this? So this is the only minimal course. So this equilibrium here, the A equilibrium, is the unique fully settled equilibrium. No, I'm sorry, did I say that right? It's the B. It's the B one. It's the B one that's the unique fully, because player 1 doesn't want to get these. Yeah, it's this one here. I should have said that way. That's coarse. Let's see, where does it say that? Last line. Only the B equilibrium is fully settled. That's right. Okay, so that's. I don't know. Is that brilliant, or is that a solution concept gone wild? I don't know. Here's the example that's where all of them, these, by the way, you know, these are not generic examples in. It's really important that I have equal payoffs. And of course, the properness was grabbing onto the fact that there was a subgame in there, and it's recognizing that there might be a subgame that forces a kind of behavior in it. And that's because the fact that there was a subgame had to do with the fact that when the other player is not putting us in the subgame, that my strategic behavior in the subgame doesn't matter. The XY is what do I do in the subgame, and it doesn't matter when we're both choosing A's. So those were not generic games that you could break those equalities, and I haven't thought about what would happen. But this is a fully generic game. Here's what's going. Player 1 has best responses 1, 1, 1, 1. What player 2 I've done from left to right. The greater probability of A, player 2 wants to choose A, but as we slowly reduce the probability, well, here's the picture. As you increase the probability of B1 from 0 to 1, first the A option is best, and then the B2 option for player 2, because this is player 2's expected utility. So she's, and then C, then 3/4. When at a half, she's indifferent between B2 and C2. When B1 is a little more likely, then she prefers C2. When B2 is a lot more likely, then she prefers D2. So she's only willing to randomize, depending on what one is doing, between either A2 B2 or B2 C2 or C2 D2. And in fact, for each of those supports, there is an equilibrium. There's an equilibrium where they randomize this way here. She's always randomizing 50-50 to make him indifferent. Player 2 is always willing to is randomizing 50-50 and all of them to make player 1 indifferent between the 1, 0, but it's this 1, 0 that matters here. It's this one here. So the only curb or absorbing block is the whole game. Curb sets, absorbing sets, gets the whole game. you could take any of those numbers and change it a little bit, take all the numbers and change them a little bit, and that's still going to be true. And it's still going to be true that you're going to get 3 equilibria that look pretty much like this. But the middle block, let's see, B2, this one here, one with the green and yellow, green and gold, I guess, is not. And one way to see it is if it were coarsely tenable, it has all of its Nash equilibria would have to be equilibria of the original game, and they're not. It has if we only thought about B2, C2, then within that looks like kind of like a battle of sexes game. It's a coordination game, and it also is 2 pure strategy equilibria. The A1, B2 within this block is an equilibrium. Yeah, 1 is bigger than 0, 4 is bigger than 3, but that's not an equilibrium of the original game. That'd be intended to deviate. So, yeah, as its block game has 2 pure strategy equilibria, everything coarsely and finable are the same thing. The minimal coarsely and finally tenable blocks in this game are the 2 outer ones, and so we get two settled equilibria in all senses, and then we exclude the middle one. Let me back up and say this came from an old paper of mine, which was just me saying I think there's something out there, and trying to guess what the hell is it. And we talked about algebraic topology. I don't really understand. Okay, so I'm hoping somebody that at least one person in the audience knows a lot more about algebraic topology of of fixed point index numbers than I do. In which case, maybe you can write the good paper. What I thought was going on was, I understand that for generic games, when you look at Nash equilibria, there's a way of assigning +1 and -1 indexes to these regular equilibria, and there's a theorem that says that the sum of the indexes has to be +1, and so that's an existence theorem for Nash equilibria. Because you can't have 0, and so you're going to hit. But if there are 3 equilibria, then you have to have canceling out +1s and -1s, and so you have to have generically an odd number of equilibria. Well, I don't understand that stuff, but I understand that the outer 2 equilibria have a certain symmetry, so they must be both the +1 equilibria and the middle, because they have the same index, and therefore the middle one, and that was true in the Battle of Sexes game. I said that I think this is an elaboration of a version of Battle of Sexes, although it isn't exactly. Jürgen had a variant of it that was more transparently related to the Battle of Sexes game. But anyway, and the +1, and maybe it's the +1 index that's the good idea. I should say I've had at least one conversation with somebody who listened to a version of this talk who does understand index number theory pretty well, and he said cheerfully, no, of course your idea of settled equilibria has nothing whatsoever to do with index number theory, but it's a good idea. I mean, he seemed to think it was, he liked the paper, even though he didn't think. So all the examples I know of are examples where my settled equilibria I like, and they seem to be doing the same thing as an index theory would do, but there's nothing intrinsic, about it. So probably maybe there's still a better paper to be written that uses index numbers. The problem is those are only defined for regular. But let me say generic properties. So the final thing I want to say, and I should shut up, and that is, so here's a formal definition. I'm going to say a game is hyperregular if for every block game, all the Nash equilibria of the block game are regular in the sense of Van Dam. And I forget what the sense of Van Dam is. And whenever I'm giving the talk, I'm on the road, and I don't have Van Dam's book with me, so I can't even remind myself. When we wrote this, I looked up Van Dam. I really should write something that I can put on the slide. I think Van Dam's regularity implies, among other things, that a Nash equilibrium has that all best responses have positive probability, and maybe that is enough. That if all the Nash equilibria of the game, if that's a weaker property, if I'm right, then I could say that that generically we know that for almost all, given the set of players, and given the set of pure strategies, finite set of pure strategies for each player, almost all games are regular in the sense of Van Dam. If you randomly generate the utility numbers, say by uniform over some positive interval, independent or multivariate normal, or some non-atomic, Anyway, that with probability 1, you will generate a game that is regular in the sense of Van Damme, that has other properties such as that all of its Nash equilibria have best responses. But you can also say, oh, I want that every block within the thing also has that property, and that's just an intersection of a bunch of probability 1 events, and so it's probability 1. So it's it's almost all games. It's an open dense set, true in an open dense set. I believe that's true. Given a fact, given a set of players and given a finite set of the finite sets, non-finite sets of strategies for each player, the set of utility functions such that NS is not hyperregular is contained in a closed set of Lebesgue measures 0. That's the formal statement. So in this sense, almost all finite strategic games are hyperregular. And if it's hyperregular, then any block is coarsely settled if and only if it's finely settled. Coarsely tenable if and only it's finely tenable. So any equilibrium is coarsely settled if and only if it's also finely and fully settled. So all of our concepts of settledness are completely equivalent for a generic class of games. We're just nitpicking, and lots of other things that we talked about are the same. That Jürgen and I talked about that we're sparing you are the same. We've wasted a lot of time I wasted a lot of time talking about the difference between coarsely and finely because, well, those non-generic games are often interesting games when you come from an extensive form game. So it's important, but in some sense, this and a whole bunch of other things don't matter. Okay, so I'm prepared to be an excited referee for papers that go more, but I'd say I'd be a more reserved referee if I could get this in. And if all you did was come up with a variant on this that's equivalent for all hyperregular games. I mean, if you could say, but Meyerson and Weibull for this reason chose the wrong thing, then then that's a good. Then of course, and the first paper, no matter what, I'm going to say, if an editor sends it to me, I'm going to say, publish it if it refers to my paper. But after that, I might get fussier. Okay, so that's it. So settledness, like persistence, but unlike perfectness and properness, is not generically equivalent to a Nash equilibrium on a finite class. I should emphasize, Ehud introduced me, was trying to say nice things about me, and said I had a paper on proper equilibrium, and that was a great idea. But one should say for a generic class of finite strategic games, all equilibria are proper. It does nothing. Perfectness and properness have that problem. But Kalai-Sammet persistence was not equivalent to Nash equilibrium. There's an open set of these utility functions for which it properly gets rid of some real equilibria, and like persistence, we also do this. And an open set of utility functions around the last example I showed you will yield games with 3 equilibria, all of which are persistent, but one of which is not settled in any sense here, and therefore we are going a little farther also, in a generic sense. That's all I have to say. Thank you for, yeah. Yeah, right, okay, yeah.
So in traversing the gap between your dynamic motivation for how sort of people eventually come to settle on kind of behavior in the stage game and the definition of a settled equilibrium in the stage game, what is the dynamic process that happens on?
Good question. Let me say, my co-author has written a lot about dynamic evolution to games, and I was hoping he was going to come up with an answer to that question. He didn't. It's it's a weak point. I don't have. I have often said let me say again. To me, one of the reasons I am most interested in literature about tâtonnement theories of convergence to equilibrium, a sensible theory about how a process of something would kind of lead you to an equilibrium, is because if we had a process for which you could guarantee that for like a large set of initial conditions or whatever, it always converges to an equilibrium, then maybe we'd find that some equilibria don't have a large set of initial conditions that lead to it, and in the dynamic, and they would then be refined away. And I think that's part of the intuition we have here. We don't have so Hart and Moscalet, for example, keep writing papers where they show that you can't do it, but then they write another paper that says that the conditions that they had in the previous paper aren't really all the things, don't conclude everything. So so it's a hard problem, but there aren't the whole literature on dynamic convergence to equilibria is missing something, and we don't have it either. Yeah. But we're talking as if we think it might be possible, but you're right. We don't know. Yeah, go ahead. Sorry.
This concept kind of reminded me a little bit of, let's say, rationalizability. And I was wondering why, so in rationalizability, a lot of times we use correlated or interim correlated rationalizability. And you are not allowing for sort of correlation. So when I think that I know the game, I'm also think that you're aware of the game. Do you think it will?
Couple of things. So certainly, we have. There's something about domination. Listen, in the relationship between our settledness and domination, is something that we've wanted to nail down better. For a variety of solution concepts that we've written down, we could prove the theorem that I wrote, that I just added to the slides at the last minute I showed you, which was that a block that the weakly undominated block, which is what people often call the rationalizable set. Bernheim and Winston and Pierce had a different idea in the beginning, but Bernheim and Pierce had somewhat differently in the beginning, but say a very nice a property we sure aimed at that's in Kohlberg-Mertens's paper was if you have a tenable, it would be nice to say if you have a nice block, call it tenable, a nice block. I'll just call it nice because I don't have a theorem. But you have a nice block of a game, and then you go to the original of the game and you knock out a weakly dominated strategy, and the game that remains, there's another nice block which is a subset of this one. We'd like to have a concept of niceness. The word we were using was tenable, in which we could prove a theorem like that. We haven't succeeded. I don't know that it's not possible. We woke up a few days every now and then thinking we had it, and then we didn't. Let me say one other thing. I think you said independence. In my paper on what's it called? Elementary dual reduction in elementary games. I talked about correlated trembles, and if you start introducing correlation, the Battle of Sexes game was an elementary game, which meant that you could make all of those. You could approximate the randomized strategy equilibrium by something by a strict equilibrium by putting in some correlated information, and when you do that, by having a mediator who correlates them with small probability of their message, and when you do that, so one thing I understood is we weren't going to get any theory that was going to refine away the randomized equilibrium if we thought about correlation. That is, by correlation, I want to say approximate a strategic form game by saying there's a small probability that a mediator might show up and send them a message, but the mediator might send an empty message to you, in which case you can't tell whether the mediator even exists or not. So if you have even a perturbation like that, I think that was enough. I might be wrong, but I think that was enough to create a game in which the randomized strategy equilibrium was a strict equilibrium of the Battle of Sexes game, and they say, oh, wow. And then it's for sure going to be a good, it's going to be settled in our sense in that extended game. So our concept, I expect, would be discontinuous with respect to changing a game by adding a mediation to it, and the payoff irrelevant, cheap talk mediation, and then reducing it back to a game of a strategic form game. Steve, question?
Yes, I guess I had a related question about rationalizability, which is that some people have looked at properness-like versions of rationalizability, including you, I guess, and but in some of those papers, it has a little bit the flavor that if you do iterated deletion, instead of looking at the sets of actions that survive, you look at sets of sets that survive, and that has a little bit the flavor of this.
I don't know.
So that it might be interested if there was a connection
This is a I'm not sure what paper you're talking about. I don't think you're talking about a paper of mine, but yeah.
Yeah, there's some stuff by Asheim and Uffenberg.
Okay. No, I should. Nope. Sorry,
And one other comment is that for the index theory, I also don't understand index
Good,
theory
yeah,
very well, but I do know that the Govindan and Wilson stuff is exploring that connection in
Yeah,
detail.
yeah.
So one interesting direction to go might be to understand via index theory the
Yeah.
connection and stability.
Yes, it's obviously I know that for the battle of sexes game must be one where the pure strategy equilibria are +1s and the mixed strategy is a -1. Actually, we've lost Jean-François Bertens. He's gone. There was a memorial service in Jerusalem earlier this year, and I saw Srihari there. I can't recall everything, but one question we discussed was Jean-François interested in this kind of idea of eliminating, and the answer was sometimes he wasn't and sometimes he was. In generalizing his, did his later ideas in this area, which were also algebraic topological, I think of him, by the way, as being a brilliant mathematician, and therefore I assume that as a mathematician he studied a lot of math, but the truth is he learned the algebraic topology that he did after writing the paper with Elon Kohlberg. He wasn't born knowing it. He wasn't even knowing it before. He learned it because he knew it was important for this stuff. But the index number part of that, as I say, some part of what he did and what they. So are they now looking at an extension which for the Battle of the Sexes game would do? And that's the first question. If I was going to talk, I'm going to sit down with somebody who's writing papers I haven't read yet, and they haven't read my paper, and God, it's hard to communicate. The first question I'd ask Srihari now that I guess I haven't is, have you and Bob Wilson written anything which for the Battle of the Sexes game gets rid of this? In which case you're now talking in my thing, and I better go study what you're doing. And I just don't know the answer to that question. I didn't ask him that when I saw him in Jerusalem. I should have, but I didn't.
Evolutionary stable strategies gets rid of it.
Yeah, that's right. But it doesn't have a general existence. That's why I've been prejudiced. I didn't mention that. Thank you.